Hello, engineers. I hope you're doing well. So, right now we're going to analyze a second example related with the conservation of mass. Remember, we have used in the previous example the different equations that we have deduced for conservation of mass related with the mass and volumetric flow rates. Yeah, and finally the material balance equation. So in this case, we're going to work with a system. Here we have this second example. In this case, it says that a steam pipe, steam is the vapor phase of water, uh, must transfer 200 mass pound per second of steam, yeah, of this substance, which is at 200 pounds per square inch. Remember that this is the English unit most common for pressure of gases, and 600 Fahrenheit degrees as the temperature. We want to calculate the minimum diameter that such pipe can have, so the steam velocity does not exceed 60 feet per second. So, in this case, I have tried to draw up uh, the pipe. Yeah, in this pipe, we will have steam as the fluid which is flowing through the pipe. We know uh, the mass flow rate of the system, 200 mass pound per second. The pressure, 200, sorry, I have omitted here a zero, 200 pounds per square inch, and the temperature of the steam, 600 Fahrenheit degrees. So we want to estimate the diameter. This diameter will be the minimum, and I'm going to explain why this is a minimum diameter. So the condition is that velocity of the fluid must not exceed 60 feet per second. So velocity must be at least what height 60 feet per second. So we want to analyze. We need to start by analyzing how does the velocity change with diameter. So if you remember our first equation, which relates the mass flow rate with the density of the fluid, the average velocity, and the area. And remember that this area is basically the in this case, the diameter of the pipe is a function of the diameter. So diameter is related with the cross-section area of the pipe. So from this equation, we can deduce a relationship which allows us to relate or to correlate velocity with the diameter. Yeah. So I have uh, rewriting this equation in terms of the velocity in order to explain this relation between velocity and diameter. Yeah. So remember that we are supposing that the cross-section area of the pipe is a circle. It is P divided by 4 per uh, times the square diameter. Yeah. So we use the relationship of the cross-section area and the mass flow rate definition, we can get this uh, equation. So if you see the velocity of this thing will vary inversely with the square diameter. It means if we uh, increase the diameter, yeah, the velocity will decrease, and in the inverse sense. So let's start supposing that the velocity, yeah, uh, has the higher possible value that is 60 feet per second. In this case, yeah, I can write or take this equation to estimate the diameter required or the diameter that it must have in order to get this velocity on the fluid. Yeah. If you see from this equation, the velocity of the steam will depend on the mass flow rate, on the density of the steam, and the diameter of the pipe. Yeah. So in this case, it's important. Here we have the density. Yeah. We need the density of the steam. So in this case, we want to use a table from the book of Sengel, Thermodynamics by Sengel, in order to look for this density. Yeah. Um, if you remember the last exercise or the last example, we use the ideal gas equation. Yeah. In this case, we can use it because steam is not an ideal gas. It has some deviations from the ideality of gas. So it is better to use the steam tables. Yeah, I have a copy here, the table A6E that you have in your Canvas LSM. Um, and here I have just copied this. This chart or this table is for superheated water. Yeah, and here we have superheated steam. So how we know that this is superheated water? Yeah, if you remember in this table, at first we have the pressure of the steam, 200 pound per square inch, and in the parentheses we have the saturation temperature for this pressure. Remember that this temperature is just the temperature at which we hope that water boils. Um, so, in this case, under this pressure, water will boil at 381.8 Fahrenheit degrees. So, if our system temperature is higher than this saturation temperature. Yeah, this is the saturation temperature. Yeah, in this case, because uh, this temperature for our steam is higher than the saturation temperature, we know that this is a superheated steam. Yeah, so in the first column, in the left side, we can read the temperature in Fahrenheit degrees. Yeah, this I'm absolutely sure that you have done a lot of times before. So we have 600 Fahrenheit degrees temperature, and in this case, yeah, we don't have directly the value of the density. But if we rewrite this first equation in terms of the density in a separate term, yeah, we have this factor, yeah, the reciprocal of density, and the reciprocal of density is the specific volume. So in our chart, we have this value, yeah, this first column of our superheated water table is just the specific volume. So in this case, we have a specific volume of 3.0586 uh, cubic feet per mass pound. So we are going to use, yeah, this value is the specific volume. So at this point, we need just to substitute the value that we know. So let me do. Obviously, we are looking for the diameter of the pipe, knowing that the velocity, or we are assuming that velocity is 60 feet per second. So in this case, we just need to rewrite this equation in terms of the diameter, or the diameter as function of all the known values. So we need to use an square root, and velocity will be in the uh, second term of the quotient. So we know that the mass flow rate is 200 mass pound per second. We have look for the specific volume for the steam, 3.0586 cubic feet per mass pound, the value of P, and the velocity that we have supposed, that is 60 feet per second. So if you do the operation, please check for that the result is correct. Is 3.6 feet. Yeah, this must be the diameter of the pipe in order to get a velocity of 60 feet per second. So, as we said, uh, this is the uh, highest possible diameter, yeah? Because if we exceed this diameter, the velocity, yeah, so sorry, this is the minimum diameter, yeah? Because the velocity reduces or reduces if we hike the diameter of the pipe. So in this case, uh, this is a minimum diameter because the diameter must be at least 3.6 feet. Yeah, we can use a 4 feet pipe or higher, and the velocity will be less than 60 feet per second. If we use a pipe with a lower diameter, the velocity of the steam will increase. Yeah, so this is the reason that we said that this is the minimum diameter, and this is the answer for example. Uh, if you have any doubt, please let me know. Have a nice afternoon.